Associate Professor David Moses is a brain-computer interface researcher within the Edward Chang Laboratory at University of California. He first joined the lab over 10 years ago as a PhD student, developing approaches to decode words and sentences from brain activity in real time. After graduating, he stayed on as a postdoctoral scholar in the lab, where he led multiple projects as part of the Bravo clinical trial to decode intended speech from the brain activity of individuals with severe paralysis as they attempted to speak. Now, as an adjunct professor, he continues to manage and coordinate cutting-edge research projects aimed at restoring expressive and embodying communication to persons who are unable to speak. Patients living with locked-in syndrome struggle to communicate due to their physical disability, despite their desire and their mental capacity to express themselves. Existing assistive communication technology can restore meaningful communication to these patients, but these devices are often slow and unnatural to use. In the Chang lab, we are developing a speech neuroprosthesis, which is a system that uses advanced neural implants and machine learning to translate neural activity into a user's intended speech. In his presentation, David will introduce the scientific background behind this technology, describe their proof of concept system, and then showcase more recent developments of their technology. In general, speech neuroprostheses offer a potential avenue towards restoring rapid naturalistic communication and expression to persons with locked-in syndrome. David's going to give us his presentation now, and that's immediately going to be followed by a locked-in syndrome person called Anne Johnson, who actually had the speech implant given to her, implanted by David Moses and his team. So we'll hear from both sides of that. Thank you very much, David. Good to see you.
Thanks again for having me. Good morning or afternoon, wherever you are. Really, it's a great pleasure and honor to be here. So I'm really excited to talk to you today about what our team has been focusing on for the past few years, and then hear a follow-up from one of our participants, Anne, who is an incredible person, pleasure to work with. So yeah, really excited to just get into this. Of course, for this audience, I don't need to preface my presentation with how important communication is. I think everyone here understands the importance of being able to express oneself and to have technology that can really enable individuals with locked-in syndrome to express themselves. And I just want to start by showing this graph where we can see that assistive technology to help patients with locked-in syndrome and patients with other forms of disabilities to communicate. And you can see that there are technologies that really can restore some very meaningful communication. And this is incredible, life-changing technology. But what we want to introduce and focus on is that the technology is slower than speech. It's a little bit less natural than speech as well. And what we want to build towards and enable is a technology that can allow anyone to communicate through speech. And how would something like this work? We coined the term, or we use the term, a speech neuroprosthesis, which is where you have a user and some kind of neural interface. So some hardware that interacts with a part of the nervous system to record brain activity. And then we can take the signals from the brain and process it through some system and then decode it into output that can then be in the form of speech and text and other types of control. And so and the key here is that this would be controlled by the person simply trying to speak. So simply attempting to speak, even if the person is unable to speak, the brain activity that is associated with those speech attempts can be decoded. And that's what I'm going to be focusing on in my presentation today. So just to give a very, very high level overview of speech, it's something that our lab has studied for over 10 years in the Edward Chang lab at UCSF. And there's approximately 100 muscles in your vocal tract. And to be able to speak, you have to be able to engage and precisely control, approximately 100 muscles at the same time. And here's some key, what we call like articulatory points of interest features that are modulated when you try to speak. And just to keep going, this is this is just, don't feel the need to read through everything on this slide, but it's just an overview to show that for actually over 100 years, people have been looking into speech. But this research in how the brain orchestrates speech has really kind of exploded in the past few decades, with more and more groups, more publications really diving into this question. And a lot of that is what's enabled us to achieve certain milestones. And this video I'm about to show you is with persons who can speak, who volunteer to be parts of our studies while they're getting treatment for epilepsy. But what we do here, and there'll be sound in a second, please tell me if you can't hear the sound in a moment, is we're actually decoding speech and articulatory movements from brain activity. Were you able to hear that?
No.
No.
No, okay. I may have to stop and reshare with the sound enabled if you give me one moment. Well, unfortunately, it told me that I have to like restart my Zoom or my PowerPoint to share sound. So I may just actually skip this. It's not absolutely necessary. Um, but basically the takeaway here is that we were able to decode from brain activity in this pattern. So these dots are representing electrodes that are implanted on the surface of the brain. And from the specific activation patterns, we were able to use machine learning and artificial intelligence to translate these neural patterns into articulatory movements that you see here, which then were used to generate a speech waveform, which is what you see down here. So a synthesized voice. Okay? And so that's the basis for some of the technology that we're working on now. But as we said, we want to build a speech neuroprosthesis, something restorative. Someone who's locked in could be able to use this, not just people who are able to speak naturally. So how do we build this technology? How would this type of technology work? And these are some key questions that were not understood about 5, 6 years ago. If you had someone with the motor cortex, the part of the brain that allows us to control our vocal tract, but you had an injury, let's say, to the brainstem, or ALS has damaged the brainstem and other parts of the brain to hinder this pathway between the part of the brain that lets us control our vocal tract and the vocal tract itself. If this part is damaged, can you still do a same approach like what I just showed you and take brain activity from this area and use it to actually decode intent? And so this is why we started the BRAVO clinical trial, stands for the BCI Restoration of Arm and Voice. It's a trial to test out new technology for the long-term restoration of communication and movement. And it's between our lab and the Dr. Chang lab and Dr. Ganguly's lab at UCSF. So our goals, from within our lab, is to study the neural representations of speech, patients with paralysis, locked-in syndrome, to validate the safety and long-term viability of our BCI approach. Here, BCI stands for brain-computer interface. It's kind of, maybe it's roughly interchangeable with the neuroprosthesis term that I introduced before. And then to develop a speech neuroprosthesis to restore communication. So these are some of our long-term goals for the trial. And I would like to, I have the pleasure to introduce on this slide our first clinical trial participant, his name, who goes by Pancho. So here he is controlling a communication device. with residual neck movements and this baseball cap and stick. And he had a brainstem stroke that left him unable to speak, to write, um, and he uses means like this to communicate. But he's still, and as we all know, um, his cognitive function was not impaired by the stroke, and he's still an extremely sharp and really just a wonderful person. And he, through a very selfless act to advance the science and the technology for the future to help patients in the future who are in a similar position as himself, he volunteered to be the first person in the study where we implanted a sheet of electrical sensors over the surface of his brain. So this is actually like laying on, not penetrating his brain, but just sitting on the surface of his brain inside his skull. These sensors that allow us to record brain activity. And this is what, this is a rough reconstruction of his brain. And here's what we're recording from. And so what we were able to build with Poncho is what we're calling the first speech neuroprosthesis. And the way the system works is, let's say that he received a prompt. How are you today? He would attempt to respond, and the brain activity that we record from this implant would then get passed through this pipeline. I'm not going to go through in too much detail, but basically it's a way to detect when he's trying to say something and to decode what he's trying to say. And this, we started with a limited 50-word vocabulary just to get a proof of concept um, system that we could demonstrate and assess. And from this, we were able to actually get some very favorable decoding, especially for an initial attempt. This is the first time that something like this had been tried before. And so here's some target sentences that he was trying to say. Here's what was decoded without a language model. So a language model is kind of like autocorrect features on your Microsoft Word or on your phone. So without the language model, just purely from brain activity, we're able to get fairly reasonable decoding. But when you include the language model, you get even better decoding. And here's an example of what the system actually looks like. So here he is getting this prompt, and now he's trying to respond by just attempting to say the words that he wants to communicate. And so those in that the responses are being detected. Like when he tries to speak, that's detected from the brain activity and then decoded into those words that you saw. And in more recent work with Poncho, and one thing I want to emphasize here is what I'm about to show you was obtained about 4 years after his brain implant. So just to emphasize as a side note, it's very stable technology, and we believe can work long term for patients, not just something that is implanted and only works for a little bit. So this is 4 years after he got the implant. We decided we wanted to try something new with him, and he is a bilingual speaker. Actually, English is a second language that he acquired after his disability. So he's never actually spoken English. Um, he used to. His first language is Spanish, and so we thought it'd be special to and very interesting from a scientific and engineering perspective to see, can we allow him to communicate in multiple languages? So again, same device, and now he's trying to say this sentence in Spanish, and it's a similar system where we're detecting when he's trying to speak, and then now we're decoding the words. And so this is about 100-word vocabulary now across the two languages. Okay, and then the same system. So that was a Spanish sentence. So the same system can be used to decode English too. He just has to attempt to speak in English. He doesn't have to prime it to say which language he's about to speak in. So the model tries to figure out, the decoders, the machine learning AI models try to figure out which language he's speaking in addition to what he's trying to say. Okay, so now I'm going to switch gears and talk about Anne, our newest participant, who you'll hear a lot more from in a little bit after my presentation. So we have this is a rough MRI of her brain, and these dots represent the sensor. So this is more channels. If you might notice, this is a newer version of our hardware that has about twice the number of channels, and Anne very graciously volunteered to get this new device implanted and to be part of our study. And with Anne, what we've done is developed a multimodal communication neuroprosthesis. And so what I mean by that is when Anne tries to speak now, in this study, when Anne tries to speak, we're decoding not just the text that you saw, so that's this stream going to text decoding, but we have three different models. These are just representations of models, and we're decoding text, audible sound, and the animation of an avatar, of a digital avatar. And so Anne was able to use a vocabulary of about 1,000 words to communicate at about 75 words per minute with about 75% accuracy. And so here are some of the sentences that we were able to decode with Anne as she tried to say them, just to give you a sense for the variety of sentences that are possible and what mistakes look like and what it looks like when the model is right. And just in the sake of time, I'll keep going a little bit fast, but here we go. Here we see some decoded speech waveforms. You can ignore these blue plots and just look, these are what the waveforms look like. And this is what or actually this is what we decode, and this is the reference. So you can see similarities between between these samples, and I'll show you some examples in a second. And then also we enabled not only this facial avatar to be animated alongside the spoken speech that was decoded, but we can also decode certain facial expressions, such as happy, surprised, sad, and also certain mouth movements. And this these charts here, if you see a strong diagonal, this diagonal, a lot of dark along the diagonal, that just means high accuracy. Okay, so let me show you, because this is the best way. Again, apologies that I don't have my sound. It doesn't appear to be working through the Zoom right now. But what we're showing here is that as Anne is trying to say sentences, we are decoding the text that appears on the screen. It'll appear down here. Also, the sound, like a personalized artificial voice that we tuned to Anne's preferences and Anne's likeness, and also this avatar that she chose to animate alongside the voice. So in those examples, those are three separate sentences kind of stitched together into one video. And so Anne had tried to say those sentences, and then a few seconds later, that's what the output looks like. And next, I'll just show you, just really quickly, these are some facial expressions too that we can decode from the same array, same thing as Anne tries to make these facial expressions. This was very preliminary, and we hope to make this far more expressive in the future. Okay, so just to start wrapping up, I just wanted to kind of discuss with everyone here a little bit about the 2-year time frame and the 5-year time frame for where we think the technology is headed. So some of the things that we really are working on now is how do we scale our technology to larger vocabularies, and how do this should enable us to scale to other languages and other things like that. We just want it to be more generalizable. We also want it to be more expressive. So we think with the avatar, it's something pretty unique, and hopefully we can facilitate more expressive interactions and control and a deeper sense of virtual embodiment. We want to continue working on the hardware. Right now, there's cables and things that make it a little non-ideal, and we just want to continue to push on this front. And this should enable us to get better performance as well with our decoding algorithms. And then finally, we just need more users to test the technology with, more amazing people like Anne and Pancho to volunteer to help us push this science a little bit further. And then just to give a little bit of beyond just our lab and our work, there are other groups working on this as well, kind of across the globe and in startup companies. There's a lot of interest from the FDA and regulators. I don't know much about the European regulators. Unfortunately, I'm sorry, I can't comment on that. But at least here, the FDA is very engaged in this technology and really wants to see it safely and reliably and responsibly reach patients. Um, Amazing groups like the group that's gathered here today are included in our discussions. We'd love to hear any feedback and to learn from you because ultimately this technology is about helping patients. And so we don't want to lose sight of that. And I just want to leave with this kind of a little bit longer sentence, but I think driven by all of this, all of these advances and these engagements, I'm personally optimistic that within the next 5 years, there may be speech neuroprostheses that become commercially available and hopefully can start to help further improve aspects of patients' lives, patients with locked-in syndrome. We want, we hope the technology can improve expression, autonomy, quality of life, and various other things, connectivity. And so I'm personally optimistic. I really hope that we do see this, and our group is going to try our best to do our part. So I just wanted to thank a few people and our funders, my PI Edward Chang and a lot of our essential collaborators and team members. Um, and if you'll excuse this plug for our trial, we are still recruiting. If you want to just learn more, there's no commitment at all. If you just want to learn more about the technology, have someone explain it to you and like all the different aspects of what I talked about a little bit deeper, then you can reach out and we're happy to give you more information. So yeah, thank you. Really appreciated the opportunity to speak today. And if there's time for questions, then happy to answer them.
Thank you very much, David. Yes, there is indeed time for questions. I think Phil's got his hand up already.
Okay, I have my hand up to clapping because David, that's an excellent work and excellent presentation.
Wasn't it?
Thank you.
Yeah, I actually have about 3 questions. I don't want to hog the floor, but I have 3 questions. One is the avatar is very, very interesting. And if I understand it correctly, the avatar is, or the camera is looking at the patient's face, and the patient is, the participant, I should say, is making expressions, facial expressions. Is that correct?
No, so it may be, we did have a camera in the video, so perhaps that was a little suboptimal. We weren't actually using the camera, it was just kind of there. So the avatar was, it's in like Unreal Engine environment, so the avatar's there, and then the patient, and the participant, and would try to make certain facial expressions, and the neural signature associated with that was decoded into the facial expression that was used to animate
Right.
the avatar. So the camera wasn't being used.
Right. Okay, so you really extrapolated the facial expressions from the neural activity alone that presumably was over the face area because your electrode is pretty wide. That's really
That's
great.
exactly right.
Yeah. I heard a little ahead of you because I heard the talk by Ed Chang last summer showing the
Oh,
avatar.
great.
I actually timed it from the time the patient was presented with a sentence to say and actually coming out and saying it, and the avatar was about 5-6 seconds. So have you any plans to shorten that time? Because that's not a conversational rate speech. So can you speed that up somehow?
Yes, actually, that's we have been working on that. That's something that we want to improve, and we have some, I think, preliminary results that are very exciting. So we just are going to try to push forward on this. So just so everyone understands what Dr. Kennedy is saying, it's that there's this delay from when Anne attempted to say something and when the decoders actually output it. And that's because we were using models that are a little bit slow. And so in more recent effort, we're really trying to get this much faster so that as Anne is trying to say something, we can decode it right then. We've done some very initial work like that before, with Anne a year or two ago. But now in our recent efforts, we're trying to refine that. And I think it's a great point, and hopefully you like what we can hopefully get published sometime soon, so that to share with the community of our solution to that problem.
Okay, just one other question. I noticed that with Sancho, you said that you did something extra with him 4 years after the implantation of the electrode, right? So the published studies show that those ECOG electrodes do not survive more than 2 years. They're giant cells and nasty histological things, but it seems like that's wrong, that maybe they do survive. Have you evidence for survival apart from Sancho? Any survival
Yeah,
data?
I mean, I think that what you're right, that there are some histological responses. So what I think the most prevalent one is encapsulation. So you have the
Yeah.
brain surfaces, and you have the ECOG array, electrocorticography array, and then there's some encapsulation of it. But from what we've seen, I think others have published on too, from multi-year, like longer than 2 years, 4 or 5. I believe first author Pels in 2019. I may be getting that wrong, but with the neuropace devices. But you can still get signals. The high gamma, which is the frequency range of interest
Right.
for us, is a little bit attenuated,
Hmm.
but you still can get signals. And so for our group with Poncho, we're using still high gamma and also low frequency signals that are a little bit more robust to
Hmm.
this tissue encapsulation. And
Yeah.
so yeah, we're still able to see. Yeah, we're still able to see. I mean, that was even more uh, a larger vocabulary than we used in the beginning with Poncho. So I don't think we've seen like this drop in performance that maybe we were a little nervous about to going in. So it's
Yeah.
pretty favorable.
Yeah. I mean, these patients can last, if they're ventilated and looked after really well, as we said earlier in the morning, they can last for years. They can survive for years. So we need electrodes that survive for years, obviously. Okay, I'll hush. Thank you very much, David. Well
Thank you,
done.
Phil. I think Frank has a
Thank
question.
you.
Yeah.
Yes, and not just years, but decades actually. But thank you. Some of my questions were covered. David, thank you for a very nice, interesting presentation. I just one more question about the usability. Is as I understood it, earlier versions had you had to use quite some time every time they want to use the system for calibration. So how is it from like how much time does it take from you start to plug the cable to until you can actually recognize
Yeah,
speech?
no, that's a really great question and a really important point. It's something that we really think like it's really essential to us when we want to test and evaluate what we're building. And the good news is that compared to maybe some other approaches, the signals we see are fairly stable, especially day to day. So we've definitely plugged in and just you know, started testing the system without any. We actually don't do any day of recalibration. So the most we would do is if we're recording 5 days in a row, then on day 5 we train or we update our models on the previous days. We don't have to do any day of recalibration. The signals are stable at least within that time frame. Like probably a long-term solution would be um, something that's automatically recalibrated, or maybe you have a dedicated little recalibration session, like maybe every week. I don't think you would need every day. And to your other point about usability, we really want to build a fully implantable device. We don't want this cable, it's a connecting. It's just so much risk. And uh, in terms of like with our current implant, we have to maintain the wound area to make sure it doesn't get infected. But a fully implantable solution can heal, and then you won't have to worry about that. And it'll be much more convenient for patients who want to use the system every day to not have to rely on someone to screw in these things and get it to work. So yeah, we're really optimistic that this will be something that will be fairly plug and play for patients in the future.
Thank you.
Okay, I think you have your hand up.
Yeah. Thanks a lot, David. Great talk. I was curious. You said that the future plans are to provide more ways of expression, and you were also talking about embodiment even of the virtual avatar. I was curious also from an ethics perspective, what does that mean to have more expression? What kind of avenues are you going to explore? And related to that, is the goal always to provide natural communication? In other words, able-bodied communication, or are you also looking into maybe more diverse ways of expression?
Wow, those are both really, yeah, thought-provoking questions. Let me see. For the first one, what we're trying to do now with the avatar is to just understand how I think that there are still some use case, excuse me, there's still some use case considerations that we are trying to think of and think creatively about. Right now, we're excited by the technology and when we had Anne work with it, one of the first motivators of the technology was of using an avatar as part of our system was to kind of, you could think of like a rehabilitation or training, not rehabilitation, but training. So you could show, please make these mouth movements, and then the user could make those, and that would help us fine tune our models. But it quickly grew into something else where Anne enjoyed using it and said that maybe for her specifically, and I hope Anne will be able to talk about this, but she's interested in using something like this for counseling, for example, to counsel others who have gone through similar experiences as her. She thought it might put them at ease or be interesting from that perspective. And so we're really trying to think like, how far can we push this in terms of different types of embodiment? And as the world is becoming more digital, we might have a stronger digital presence, in the coming years. I'm not trying to predict any metaverse or anything like that, but there's just a variety of applications and value, I think, in being able to have control of a digital avatar, and then maybe we can think about applications from there and how we can relate that to improvements maybe in the physical world. And it's still fairly early and we're open to suggestions, but right now we're just trying to explore the space. And then I would say for your second question, we have been focused on speech and on eventually like control of a computer and things like this, but I hadn't thought about completely novel ways of control that are maybe not that are more typical to like maybe folks who are locked in and I mean we know the assistive communication technology and we know these, but yeah, I'm curious, maybe one day we can talk about what you had in mind, if you had anything in mind. I'd love to brainstorm a little bit.
About music, have them play music. We did that with
Oh yeah,
yeah, it's cool. And Dick would like that.
right.
Yeah.
Dick would love
That's a
it.
great idea.
We actually did it. We had the patient sitting there in this, the neurotrophic electrode, and the signals would come in, we'd attach them to notes, and he'd just sit there playing music. He loved it.
Right. And we've looked in the pitch before, you can have some, that's only maybe one step away. Yeah, it's great.
Do you have a question, Tina?
I just wondered if in the future, if there's a possibility that this would be a non-invasive application.
Yeah, that's another really great question. I personally am not optimistic about non-invasive options. They're very limited in the types of signals that you can get. I would say probably there's one that is being kind of looked into very heavily right now, both in academia and industry, which is like facial EMG. So you could put EMG sensors along the face and try to detect very residual movements and the muscle activation associated with very, very minor, maybe even imperceptible movements to see if you can translate that into decoded outputs. That's interesting. EEG technology is getting a little bit better. I would say year by year. I think it's there's still promise there, but I just don't know if you'd ever be able to like what Anne was able to achieve. I'm not sure what a non-invasive method to achieve that would be. Other people are also looking at ultrasound too, by the way, like ultrasound sensing, but these things are it's really difficult to get the same level of signal resolution that you're able to get by going inside the skull, fortunately. And so we hope that with our approach, where you don't have to penetrate the brain, that maybe it's still invasive, but it might be some kind of middle ground. But I think yeah, I'll leave it at that.
Thank you.
I
Thank
kinda
you very
like
much, David. You got something to
Sorry, Tina, it's kind of like who's afraid of the big bad wolf? The big bad wolf being us who do the invasives. But we've done 6 patients, right? 6. And there were, except for me, but they were all implanted with electronics, single channel, not great, but they all had electronics and we had no problems. The only problems were the electronics broke down, so we had to replace them. But once you cover it up totally, and as David was saying, they're trying to do everything implantable. It'll just be, I mean, you have cardiac pacemakers, and everybody wants a cardiac pacemaker. Who needs one? There's no hesitation. Previously, there was electrodes stuck through the chest wall into the heart, and if it fell out, they died. Now they said, well, we've got to have, I can tell you the whole story about that, but basically, it's going to be just as natural as cardiac pacemakers. And David is absolutely right. In 5 years or so, it'll be pretty much routine. I imagine that when patients come in to the hospital locked in, they get implanted in the first few days with electrodes and they'll start speaking right away. That's what that's what I foresee.
Yeah.
That's the dream. That's the
That's
dream.
incredible.
It's going to be reality, David. You'll see.
That's incredible. And what is the cost related for something like that?
Okay, the cost. In our system, we estimate about 150,000 for the whole lot, including the computers and so on. And we've estimated how Medicare would pay for that, since it saves so much money, patient care and loss of income from lack of employment. And so Medicare eventually will pay for it. In the US, I'm not sure about Europe, but it sounds like, from what I heard today, that the systems in Europe are very free and easy with money and they get looked after. So, but I'm not sure, David, you could answer the question from your point of view.
No, I think that sounds really reasonable. There's not much precedent, as you might imagine, in the market right now. But if you look at the unfortunate story of Second Sight, which was a retinal trying to restore vision, that was about 150K, and they get Medicare, CMS. Like this is in America, at least. I don't know if it ever made it to other continents, but to other countries. But that, even though that company wasn't successful, like you can still learn that $150,000 was fairly reasonable, and for with reimbursement, so that patient will not pay that much, not close to that much. And so we are, optimistic that it's exactly as Phil says. There's so much potential to ease burden on the patients, ease burden on caregivers, to restore productivity to the patients. We want them to be able to do the same things that we can, and not be limited by their technology that they have available right now. Like, there's no reason that they couldn't, as so much of the workforce is digital now. Like there's so much value, I think, that we can have just from that, in addition to them being able to communicate with their loved ones and all the other like extremely important personal personal features that we want to have in the technology. So yeah, I agree with that take.
Great. Thank you very much on that very positive note from you as well, Phil, how the future's looking with, as you say, with the heart transplant, heart pacemakers and so on. They're just a part of medical procedure now. So it's likely to happen in exactly the same way with brain things. Thank you very much, David. it was really good to meet you. Thank you for coming. You can go and rest again now because it's like the crack of dawn in your country. I'm so sorry to get you so early. But thank you very much.
No
So
worries.
we'll